Alright, so this is NCCER Instrumentation 4, Module 5, PLC, or Programmable Logic Controllers. So, I probably get asked like how much people learn about PLCs and stuff and instrumentation more than anything. And I tell them like there's one chapter on PLCs and instrumentation. Even though, like, if you guys can get into instrumentation and work your way, and you find somebody that's intelligent in this stuff, learn as much as you can, because this is where the money is. What's that? If they're good, like not in, like that's what, like you can say electrician and you can talk about like a 19-year-old kid pulling wire in a house. Then you can say like a shift electrician in a plant, and sometimes, especially where you work, they're only going to touch like electrical buckets and MCCs and stuff like that. They're not like, but then again, like I was called an electrician at Nucor at the steel mill where I worked, and I was in PLCs every day. And I wouldn't do I didn't do any of the kind of bending or basic level. Like I was an I&E electrician that we were very heavily into PLCs and stuff. PLCs are very good for helping troubleshoot because and they're everywhere. Like this, that's the big newer Allen Bradley one. But just before I forget. But yeah, there is. I do have, like most of y'all worked on the electric motor control trainer. It's got the panels that you can move around and stuff. And I've got a panel coming sometime in March from them that's got a PLC on it. And you'll do a little bit of stuff, so you'll get a little bit of interaction with a PLC. But it's really something you got to spend quite a bit of time in. But if you can get well versed in this stuff, it's super valuable, and it's actually it's part of the thing that I enjoy the most, rather than just pulling wires or I mean setting up instrumentation loops is fine, but PLC can be a fantastic paying job. Going through the trade terms. Human-machine interface, like you probably have heard that before. HMI, that's just what the like an operator or whatever is looking at, TV screen, but touch screen that they can change stuff. I do have input-output highlighted. That's the component of the computer or PLC that allows it to interact with the world. So all of these PLCs have different slots, and they have. Like this is the input-output card, and literally all it is it has two different Ethernet ports. Because this isn't, this rack doesn't have a processor in it, so this doesn't have a brain. This would just be like a remote rack where they would send stuff, and then you would run an Ethernet cord back to your main. Like there's a whole nother rack of this that you would run, and it would communicate all the information off of all these cards back to the main one. But they do that by way of input-output communication. But you also have, see how it'd be confusing, because you also have input and output cards. So I have like a DC input card. Yeah, DC input cards, DC output cards, relay output. They also make, this one has a ton of analog input cards. So for all of your like level and flow and stuff like that, that's not a 1 or 0, it would go into an analog input card. But just knowing that all these are called I/O, input and output cards. Modules, I guess I just call these cards, but modules are, I guess, are technically what they're called. My next highlight is in 110. Typical PLC systems, first sentence is highlighted. A programmable logic controller is a microprocessor control device similar to a computer that can be programmed by the user to perform specific tasks. Let me just make sure. Yeah, I want to make sure I started that. Immediate next sentence is a separate highlight. Unlike an ordinary personal computer, however, a PLC is ruggedized and suitable for industrial setting. This doesn't mean that these are going to sit out on the factory floor and stuff like that. These are still going to be in a control room inside of a cabinet, air conditioned, but they're just a little bit more hardy than a regular computer. Next paragraph, top right of page 1, first sentence is highlighted. The term architecture is usually associated with building designs, but in PLCs it refers to how the whole system is put together. So whenever you're first like installing a PLC, like this whole the back of this is called the back plane, and then I can plug these in. I can move these all around to different slots and stuff like that. But whenever you're setting stuff up inside the program and stuff, you have to physically say slot 1 is a DC output, slot 2 is a DC input. You can't just put these in randomly and it automatically knows. But that's like called setting up the architecture. You're setting up where stuff is on the back plane, so it knows where to talk to different types of cards and modules. Skip a sentence and the last sentence of that bullet point, or last sentence before the bullet points is highlighted. The following are a few of the things that they consider while designing and building PLC-based control systems. And then the last bullet point is highlighted to go along with that. The types of human-machine interface used to interact with operators. In 111, examples of PLC systems, kind of two separate highlights that go together for one. You just need to know, I think it's this third sentence, figure 1 shows a micro PLC that's a complete standalone unit, and then that goes along with the last sentence in the paragraph. PLCs of this type are common in situations where some intelligence is required, but large amounts of input-output is not. So you usually, I think I have one of these in my attic somewhere, but usually you're putting your inputs on the top and then your outputs on the bottom. So this would only have 4 outputs on it. Whereas, like this first DC output card, has 35. This is called a Slick 5000. That's a micro PLC. So that would have 5 outputs versus 30 something in one card in the big one. But this would be like, use these to set up like very small machines that only do a couple different things, and that way you're not spending. Take these. This is $4,000 for just the module. Like the whole setup is tens of thousands of dollars. And then I think the program, in order to program it, is $3 grand a year per workstation. Like they're paying a crap ton of money for these. Whereas you could have usually we had a laptop that we could carry around and stuff, and then you could just program these. And these are cheap. You can get those for very cheap. And that one's Allen Bradley, will be a little bit more, but you can get even like a Automation Direct one for under $100, which is nuts. But that's a micro PLC. Flipping over to page 2. First 2 sentences on page 2 are an online test question. A typical medium capacity PLC system is shown in figure 2. The particular system is a rack mounted and can be expanded with up to several thousand I/O connections of various types. So that's the medium. Usually, like if that's an Allen Bradley one, which I think it is, it's called a Slick 500. And then the large one, like this one, is called a Slick 5000. So medium, you need to know that medium can handle several thousand I/O connections. The next paragraph, the whole thing is highlighted. Figure 4 shows 2 examples of HMIs, one of which is very large and sophisticated, and one is very simple. Button switches, lights wired on the panel or control box can function as HMI as well. Each HMI must be tailored for the specific application. They must also be designed with ordinary operators in mind rather than experienced technicians and programmers. A good HMI requires very little instruction to be used effectively. That's a big thing. If you ever get into designing this stuff, you have to realize, like I've had to realize several times, like people don't think the same way that I do. And you have to create these different graphs and stuff like that in order for like somebody very basic or new to be able to run this stuff. And I've seen people that do stuff that's super complicated that makes sense to them, but it doesn't make sense to just an operator coming in and trying to do stuff. This one's pretty well done. Just a very, very simple way of explaining how this works. Like if I was all of these pictures are like base pictures inside of the program to make this. Like they make tanks, and then they have little pieces of automation. So you insert like this, like you can see the level of this tank, and all I'm doing is everything is a tag-based system. So for this level would be an analog input probably coming from a differential pressure sensor off of the tank. So an analog input, it goes into an analog input card in my PLC, and then once I'm designing my PLC, I create a tag that says that's for tank 5 level. And then I create my image, and I can put my automation on there, and I drag my tag to that specific point, and now that tag is associated with what's going into this card, and it raises and lowers based on what's going into this. So that would be an analog version, and then you also have like start and stop. If this was a pump, that would be a digital input. So start and stop would either be on or off, right? But you can have like the right hand side is, I mean, that's super low as far as like actually human machine interfacing. Like they would even call like the trainer right outside the door, the process meter that's over on the side, that would be considered a human machine interface, because you're not doing, we don't control with that other than alarms. It's just mainly used to look at the level of the tank or flow. Hardwired systems versus PLC systems. First sentence is highlighted. The primary hardware component of a PLC, primary hardware components of a PLC are the power supply, the processor, I/O modules, and communication modules. So just running through this big one that's up here. Power supply is all the way right here. Like I said, this one is not, this is kind of like a slave backplane that connects to another PLC. So this one doesn't, normally your processor is in slot 1. This is slot 0, slot 1. Like the power supplies don't come off of here like the other things do. And then you have your input, all your input output cards, and then you have your I/O modules that communicate with other stuff. The rest of that paragraph is another highlight. A personal computer is often used to program the processor, but is not considered a primary component because once the processor is programmed, the computer is disconnected. So you have to have a computer in order to program this, but that's not considered part of the hardware of a PLC. Hardwired circuit 121. I don't have highlights in that, but you can see like this would be an actual hardwired circuit. So ladder logic, I think everybody in here can read this at this point. I got 2 normally open switches. Push the switch down to turn on the lamp, switch 2 down to turn on lamp 2. If I'm looking at a PLC controlled unit, like if I ever wanted, so say I wanted my hardwired unit, say I want switch 1 to turn on both lamps and get rid of switch 2, right? I'd have to physically go in there, unwire, take this wire off of lamp 2, get rid of the switch, and then run a wire from lamp 2 to switch 1, right? Not that complicated, but it still would take a little bit of time. If I go into my logic of my PLC, all I would have to do is drag and drop a few lines, and then automatically switch 1 turns on both lamps. Like it's a matter of this takes 30 seconds, whereas this might take half an hour for somebody to go get inside a panel, change stuff up, shut power off, and whatnot. It just, PLCs make stuff way easier. My highlights in the, I don't have any highlights in 121, but in 122, the PLC controlled circuit, the sentence that splits the columns is highlighted. As you can see, the switches are not connected directly to the lamps. Instead, they are connected to an input module. So out to the side of that highlight, I wrote controls lamps indirectly. Because essentially what's happens if I want to turn on lamp 1 with switch 1, I push switch 1, that goes into a digital input module, because switches can only be on or off. The processor quickly thinks, if I get this input, then what do I need to do and turn on this output? And that happens, the processor thinks in quicker than you can blink our eyes. Like, that happens super quick. It's not necessarily, it's not as slow as I'm saying. The rest of that paragraph, the last 2 sentences of that paragraph, are a separate highlight in the top right of page 3. The lamps are connected to an output module. The input modules and the output modules do not communicate with each other directly. Each is controlled by the processor. 1, 2, 3, comparison of a hardwired and PLC systems. Third paragraph, last 2 sentences are highlighted. Many PLC input modules use devices called optocouplers to separate the inputs from the processor. These devices can protect the processor from voltages up to several hundred or even several thousand volts. That's just the last 2 sentences on page 3. Moving on to page 4. You can see I'll give you my highlight, then I'll talk about stuff. Third paragraph on page 4 is highlighted. The advantage of a PLC becomes evident when circuit changes are required. For example, in order to change circuits of a hardwired system to have switch 1 control lamp 2 and switch 2 control lamp 1, it would take several minutes to rewire them and involve moving wires. With a PLC, a simple program edit makes the change with no rewiring needed. Got ahead of myself. That's exactly right. Not exactly what I just said, pretty much. Out to the side of that paragraph, write flexibility. Flexibility. So you have flexibility with the PLC, because I don't have to. Maybe the wire wouldn't be long enough to connect to switch 1 to lamp 2, and like I have to go get new wires. Like in a PLC, it's drag and drop. So I don't think it needs a picture. So if you look still on page 4. Figure 8 would show a hardwired VAT control. So this is what you would see whenever you're like wiring up the electric motor control. You've got a pressure switch, a temperature switch, manual override, and a motor starter. Whereas in a PLC, you're just going to see normally open and normally closed contacts, because all of those switches are they digital or are they analog? Digital, because they can only be on or off. So you only see, if you look at that figure 9 on page 4, you're only going to see normally open contacts. And if you're looking at a PLC program, whenever they close, they light up green on there, but those tag numbers are what are tied to those digital inputs. So that's digital input 0, 1, and 2, and then outputs are written as circles. So my output would be my motor starter, so that would be my signal going to my motor starter to kick that on. So inputs are written as just like normally open or normally closed contacts. Outputs are normally written as circles in a PLC program. Take a second and see if you can answer those 5 questions on page 6. So, section 2. No, section 2 was on first one. We done binary numbers before? I feel like we have. I mean, very little. Maybe not. I forget who I've gone over stuff with. So you're gonna need to know how the binary stuff works. I know you had a little bit of it in the digital logic circuits, but kind of have to know how that stuff works for this chapter. Binary numbers 2, 1, 0. I've got the sentence in between the 10 to the third, 10 to the second, and then the 2 to the 7. With binary, each column added to the left is an increasing power of 2. So if I had, like they have like the 8 columns of binary, but binary is a base 2 system, right? Because it can only be 0 or 1. It's a base 2 system. So in binary is read from right to left. So if I'm reading this from right to left, I have a 1s column, 2s, 4, 8, 16, 32, 64, 128. Right? And I can have, these are each called like bits. These would be bits if I'm putting binary in here. And then I'm just, those bits put together, you can have a 4 or an 8-bit word to create different numbers. I do have the 2 to the 3 column, which is the 8s highlighted, and the 2 to the 2 column, which is the 4s column highlighted. 211, converting binary to decimal. I've got the whole second paragraph highlighted. Going into page 8, converting from binary to decimal is fairly simple. If a 1 is present in a given position, the column value for that position is added to a running sum. If a 0 is present, ignore the column value and move on to the next position. In other words, find the decimal equivalent of a binary number, multiply each digit by its place value's corresponding power of 2, and then find the sum of the results. For example, to convert the binary number 101101 to its decimal equivalent, use the following process. So, and then I've got the process highlighted. Anytime you see, like it says 101101 and it's got the little 2 beside it, that's saying that that is a binary number. That's not just 101,101. That's saying that is a binary number. So, like you can do their power of 2's steps, but to me it makes more sense if you just write out the columns. So my first column is always my 1s. Remember, we're going from right to left. 1s, and then you're doubling every time for 8 different columns. So 1s, 2s, 4s, 8s, 16s, 32, 64, 128. So that's 8 different columns, right? And they're saying they want to convert the number 101101. So 1011. Then we have 6 numbers in there. So if you only have 6 numbers, you're assuming that your first 2 are zeros. So that's my binary. So then you're just bringing down what you have and adding it together. I don't have any 128s, so I have 0 of those. I don't have any 64s, so I got 0 of those. I got a 32, no 16, I got an 8, I got a 4, and I got a 1. So essentially you're just adding all of this up and adding zeros. 32 plus 8 is 40, plus 5, I mean it's on there, but that's 45. Does that make sense to everybody?
Yeah, but why does the 45 have that little 10 by it?
Because we are converting it to decimal.
Okay. Okay.
And our decimal, like that's our regular numbers, right?
Right.
Base 10, because we count to 10, and then you go to a 2-digit number, and so on. So that's, if you see 2, it's binary. If you see 10, it's decimal. If you see 16, it's hexadecimal. Okay, and we're going to talk about those. So just a little bit of practice. Convert my number. Convert that to decimal.
We read those numbers right to left too, or just the columns?
You read, if it's in binary, you're reading it from right to left. that?
That would be 10.
What would be 10? Yeah, whatever your decimal number would be base 10. Alright, what'd y'all get?
237.
183.
181.
Alright, let's go through it. I got 183. I'm not positive I'm right, but going through it. So, this is the what column? 1. So we got a 1. This is the 2's column.
0, 4.
4's column.
8.
8's, we don't have an 8. We have a 16.
32.
We have a 32.
120.
And we have a 128. So all we have to do is go back and add all those together.
48, 7, 50, 85, plus 128.
55 plus 128 should be 183. Does that make sense? Anybody not see where they messed up? Alright, I'm gonna do one more. Convert that one. 1100, 1100. Right off the bat, is this number going to be odds or evens? So whenever y'all take this test, give yourself that chance. If the last number is a 0, it's going to be even. If the last number is a 1, it's going to be odd. So usually you can mark off 2 answers on the test just by knowing whether it's odds or evens. What'd y'all get?
204.
204.
204?
10 base.
Alright,
Base 10.
204. Ready? Everybody go with that? Alright. Moving on. 212. Decimal to binary conversion. So, going from decimal to binary is a little bit more difficult. You gotta do a little bit more work. I have steps 1 through 5 highlighted. You're gonna have to do this in one of the reviews. I'm gonna read through the steps and then we'll work through one of them. Step 1, determine the largest power of 2 that is still less than or equal to. They're doing converting 47 decimal number 47 to binary. So less than or equal to 42. It is 32, which is 2 to the 5th, because the next power of 2 is 64, which is larger than 47. Step 2, subtract the 32 from 47 and write down a 1. This will be in the 32's place of the binary number. The result is 15, so you got 15 left. Go to the next lowest power of 2, in this case 16, and subtract it from the result in the previous step. Since 16 cannot be subtracted without a resulting negative number, write down a 0 in the 16th place, a binary number, to carry the 15 to the next step. Subtract the next lowest power of 2, which is 8, the result is 7, because this is a positive number, write a 1 in the 8th place. So repeat this process until you obtain a result of 0. The 1s and 0s you record are the binary number. In this example, 4710, which means it's digital, converts to 101111, base 2. So, let's work through one of these. Keep the number up there. What number y'all want to convert? $182.
1011110.
All right. So 182. What's my largest number in my slot that'll go into that? 128. So I put a 1. Like the easiest way for me to do this is to write down all of these and then write 1s and 0s under it. All right. So I'll get a 128 in there. Right. So 182 minus 128 should get 54. Right. So my next number that's going into 54. Will 64 go into 54?
0.
Will not. So I write a 0 in that column. Will 32 go into 54? It will. So I write a 1 in that column. Minus 32, you get 22. Will 22 go into 16?
Yes.
Wait a second. Oh yeah, will 16 go into 22? I asked it backwards. Yes. So then you got 16 left. Leaves you with 6. Will 8 go into 6? Nope. 4 will. It'll leave you with 2. 2 goes into 2 one time. Minus 2, have a 0. 1 doesn't go into 0. So, I mean, you can see it spread out, but 1, 0, 1, 1, 0, 1, 1, 0, base 2. All right?
That's always base 2.
If it's a binary number, it's base 2. Let's do 106. Convert that to binary.
Skip 32.
Huh?
Skip 32.
That's the 32.
You get 42 minus 32.
Oh yeah.
6 minus
Oh, okay.
64, which is 42.
Alright.
right? So if you end up with a remainder at the end, you did it wrong. Like it's easy. I don't do this stuff all the time, and you won't have to do this all the time. But it is good to know if somebody's talking about this, because most of this is in ones and zeros. So working our way through this one. I got 106 base 10. Is 128 going to 106?
No.
Nope. The 64? It does. So you minus 64, and that'll give you 42. Does 32 go into 42? Yep. Leaves you 10. 16 does not go into 10. 8 does. 8, I have 2 left. 4 doesn't go into 2. 2 does go into 2. 1 doesn't go into 0. 0, 1, 1, 0, 1, 0, 1, 0, base 2 is the same thing as 106 base 10. Everybody all right with that? All right, let's continue on. Hexadecimal numbers. 220. 220, first sentence. You'll have 2 questions come off of the first sentence on page 9. Hexadecimal, which is base 16, uses 16 digits. So they use 0 through 9, and A through F to represent numbers. Hexadecimal to binary conversions. I have everything in 221 highlighted. I'm going to read through it real quick, and then we'll walk through one just briefly. To convert binary numbers into hexadecimal, divided into groups of 4 bits, starting from the right side. If the number of bits isn't easily divisible by 4, add sufficient leading zeros to the left sides of the binary, the side of the binary number to make it so. Next, using table 1, convert each group of 4 bits into an equivalent hexadecimal digit. After a while, you will have these memorized and you won't have to use a table. For example, to convert the binary number 1, 0, 1, 0, 0, 1, 1, convert that binary number to hexadecimal. Proceed as follows. So they split it into 4 bits. So each one of those 4 bits then correlates to a hexadecimal number. In my mind, like, you're not going to have a hexadecimal, well, you're going to have a phone on you if you wanted to pull up a hexadecimal to binary number. Like, you're going to find a converter and just type it into your phone and it's going to spit it out. But you're also not going to have a table 1 next to you. In my mind, to do this, I have to go to decimal first. So I have to go from binary to decimal to hexadecimal. So my first word, or my first 4-bit numbers is 1010, and then that is equivalent to the decimal number. If I look at 1010, that would be 8 plus 2, which is 10, right? 10 in hexadecimal is my first letter, which is A. So that would be the first 1010 would be A, that's what it shows in the table 1. And then so on and so forth. The next paragraph, to convert a hexadecimal number to binary, use table 1 and convert each hexadecimal number to its 4-bit equivalent. Do not drop leading zeros. For example, to convert the hexadecimal number E59C, which has got 16 to show that it's base 16, proceeds as follows. E in that table represents that binary number of 5. Like it's easy to do if you have a table sitting right there beside you. And you guys will have the table. You'll have one practice test question on this and one section review question. Use the table. I think they give you the table on the... They did not give you the table. Don't make that hard. So let me just do one hexadecimal to binary. The first thing if it were me, the first thing I would do on a scratch sheet of paper, if I was taking this test, is write that at the top. I mean, it's easy, because you know, most of the time they're going to keep it in 8-bit words. These they're splitting up into 4. So, E59C16. E59C base 16. Alright. In my mind, I know that 0 through 9 in hexadecimal is just 0 through 9. And then 10 starts with my first letter, and in hexadecimal I go A through F. My maximum is 15. Because I go 0, I start at 0 and then I go to 15. That's 16 numbers, but it's base, and that's why it's base 16. So A is 10, B is 11, C is 12, D is 13, E is 14, right? So E is 14, this is 5, this is 9, and C is 12, 10, 11, 12, 12. Alright, so I converted these into decimal, and now I want to convert them into binary. So 14 in binary is, I know I need an 8. I need 8 plus 4 plus 2 and no 1. It's 8, 12, 14, no 1. Does that make sense? So that would be 1, 1, 1, 0. 0. 5 in binary would be just 4 plus 1, so it would be 0, 1, 0, 1. 9 in binary would just be 8 plus 1, so it would be 1, 0, 0, 1. And then 12 would just be 8 plus 4, so it would be 1, 1, 0, 0. Am I going too fast for that, or is that, like, are y'all go with that? So this would be the binary equivalent of that hexadecimal number. Alright. Take a break on that and go to 230. Binary codes, going on to 231. I still got a lot of highlights on page 9. ASCII, the whole first paragraph is highlighted in 231. One of the most useful ways to enhance human-computer communication is to work with letters, numbers, and symbols. In other words, text. While some computers internally handle all the information as binary numbers, it's helpful if HMI devices work with text. For this reason, schemes that represent text as binary numbers were developed in early days of computers. One of the oldest and still most commonly used is ASCII. It's just a computer coding program. The next paragraph, the beginning is highlighted all the way through the sentence that has control code. ASCII stands for American Standard Code for Information Interchange. It has 7 or 8-bit binary code in which each number represents a standard character of some kind. Early ASCII systems use 7 bits, giving a total of 128 possible characters. Not all of these corresponded to visible characters. Instead, some acted as control code that modified the behavior of certain types of devices. Skip a sentence, and I've got the second to last sentence on the page highlighted. Many computer manufacturers later added an 8th bit to the ASCII standard, which made an additional 128 characters available. Page 11. Binary coded decimal. BCD. I think I talked about this for just a second from the last chapter. You're going to have a couple of different questions. Like BCD is not hard, but it does make all the other ones more confusing. My second and third sentence in 232 are highlighted. To convert a number from decimal to binary coded decimal, each decimal digit is simply turned into its equivalent 4-bit binary number. To convert a BCD number back to decimal, it must be broken up into 4-bit words, or excuse me, 4-bit groups. Last two sentences in that paragraph are also highlighted. For example, the decimal number 127 base 10 equals the BCD number that Similarly, the BCD number of that equals the decimal number 979876. So, how this is done, if I wanted to convert number from decimal to BCD. So, decimal number we'll say is 128, right? In order to convert this to binary, if I was converting this just to binary, I would write 1 with 7 zeros, right? Binary coded decimal, you're splitting up each number by itself and writing a 4-bit binary word for it. So my first word, my first word is going to be for 1. How do I write 1 in a 4-bit binary number?
00001.
And again, too many zeros. 0001. So 0001, right? Because all I have is 1 in that column. How do I write a 2?
0010.
How do I write 8?
1000.
1000. And this would be B, C, D. So see how it's easy, but it makes stuff more confusing. Everybody good with that? Like you'll have a problem or two to do that with, but that's binary. 233 gray code. First sentence is highlighted. Gray code is a modified binary code used by rotational or linear motion encoders to convert motion positions to a digital value. I do have, well, table 3 is highlighted, but you'll be able to do the BCD from that. Yeah, so I should get an encoder. An encoder is used on like anything that spins. So like a lot of cranes use encoders, and they put that on the big spools and stuff like that, and it just attaches to something that's spinning, and they can write the code to determine like how many feet of line do I have out or something like that. I had to put an encoder on, like we had just a very basic cutoff section in like we made the big coils of steel. Sometimes they knew that the first 20 feet of the coil was bad, so they were going to cut that off before they sent it to the customer. So they had a little station, and I had to put an encoder on the end of the little wheel that spun, so they then changed that into a footage. But they use gray code inside of encoders. See if y'all can answer those 6 questions on page 12. Alright, section 3. Going back to the PLC side of stuff. PLC hardware. I've talked about addresses and how each bit by itself, or each normally open or normally closed contact or output is addressed whenever you're creating new code. I don't have anything highlighted. You will have highlights in non-volatile and volatile memory. A scan. So a scan is you have all of your PLC code. So tons, like tens of thousands of I/O modules, written code. A scan starts at the top of the code and goes all the way through. A scan happens like that, but that's how a PLC reads it. Like it scans it, and then scans it again, and scans it again, and scans it again, and it's looking for changes. It's looking for changes in I/O so that the processor can make changes to the out. It's looking for changes in inputs to make changes to outputs and stuff like that. But a scan is just reading from top to bottom, and it does that super fast. Said we'll talk about volatile memory. 310 power supplies and grounds. Second paragraph on page 13. Second sentence. For very small PLCs, the power supply is often internal. So that little micro PLC that had an internal power supply like 12 volts is usually, 12 or 24 volts is usually powering those up. Sentence that starts on page 13 and continues on is highlighted. The voltages used by electronic devices found in most modern control circuits are very small, often 5 volts DC or less. The next, I did start that back up, right? Yep. The next 2 sentences are a separate highlight. Static discharges from improper handling can destroy them. Static discharges are stray voltages from the process equipment, processes, non-process activities such as welding can destroy electronic devices if they are not properly grounded and shielded. A lot of, what's our most common instrumentation signal? Most common transducer. Signal. What to what?
Zero input.
Huh? It's analog. It's a current input. What current? 4 to 20. 4 to 20 is our most common input, right? So talk about shields and our instrumentation cables and stuff like that. Like this is where you're shielding them right below this. Like you're bringing your instrumentation cable into these analog inputs, but you're shielding them somewhere down below because those little stray voltages from a power line feeding into this can mess this stuff up. Process modules 320. I don't have anything 320, but processor memory 321. This is where you're gonna have the 2 highlights in volatile and non-volatile memory, and you need to this is usually the higher miss questions, so make sure you have the difference in your head. I've got the third sentence of 321 highlighted. The program itself usually resides in non-volatile memory so that it won't be lost if power goes down. So non-volatile memory is what stays in the computer, right? The rest of the paragraph is a separate highlight. Volatile memory contains data and other temporary information that a PLC generates and uses as the control program runs. So this would be like, say your PLC was running, your plant or whatever piece of machinery is running, and in the code somebody's pushed start on something and there's a digital input that has a 1 written to it. If power goes off, that 1 doesn't, whenever you bring power back up, that 1 doesn't stay. That on doesn't stay, like it resets back to its normal memory. Does that make sense? For the time being, like if stuff stays on, that volatile memory is written down in there. But if power goes off, it gets rid of volatile memory. Last paragraph on page 14, first 2 sentences are highlighted. The PLC's memory is organized into various areas depending on how the processor uses the data. This organizational diagram of memory is called a memory map. That's once you get in, like, the memory maps are crazy once you go into like the data catalogs and stuff like it literally looks like the beginning of the Matrix or something like that, where it's all 1s and 0s. Whenever you get into those memory maps, like, unless you know what you're doing, they don't make sense, because it just looks like a full page of 1s and 0s. Page 15, the little paragraph after the paragraph of data table, that little paragraph is highlighted. Whole thing. All data is stored in what's called a data table, that's what I was talking. The data table is divided into 4 areas: the input table, the output table, internal storage bits, and storage registers. Paragraph in the bottom left of 15, first sentence is highlighted. Storage registers hold larger chunks of information, which is called words. So rather than just holding 1s and 0s, they can hold a word, which is a 4-bit binary word. Flying down the hallway. Processor scans 322. I probably already said what this is about to say, but the first, I think 3 sentences, all the way beginning all the way through the word scan is highlighted. The processor module controls the system by executing the control program. During program execution, the processor reads all the inputs evaluates and acts upon them according to the program logic, and then modifies any outputs affected. The process of reading the inputs, executing the program, and updating the outputs is known as a scan. Page 16 and 17. Input or I/O communication modules. So 331. So these are the modules that I was talking about. 331 talks about, like, you can have discrete, which would just be ons and offs, numerical data, analog, special. You can have special modules. So if you have thermocouples and RTDs, you have to have a special card for those. Like they have to change from, like if it's a thermocouple, they have to change from those little millivolts into a usable signal. So you have to have a special card, and it literally says, I don't think they even do that. They say thermocouple or RTD on the front of them. I don't have any highlights in 331. 332, discrete modules. So these are the ones, discrete, ones and zeros. Right hand side of page 16, second paragraph on the right hand side, last sentence is highlighted. The power and logic portions of the interface device are electronically isolated from the processor to prevent damage from noise and power surges.
Where is that at?
Right hand side of page 16, second paragraph, last sentence.
Right before the modules.
Shit. On page 17, I've got an online test question marked for just the heading of 333. That's all I have marked, so I'll be looking for y'all to say something when you're taking this test. I need to put another highlight in there. If you get a question on your test, whenever y'all take this next week, that's about numerical data interface modules, I want to see it so I can fill out my highlight. But there's probably going to be one based on that. Analog modules 334. The last paragraph of 334, first sentence is highlighted. An analog output module receives numerical data from the processor, which it converts into an equivalent voltage or current signal with a digital to analog converter. A lot of times you have way more analog inputs than analog outputs. I mean, you still have some analog outputs and stuff, but most of the time we're looking at a 4 to 20 signal coming from like the level of a tank or the flow of something. We're looking at something, and then based on that, a lot of our outputs are digital, because what we're outputting is usually turning on or off a pump, on or off a solenoid, something like that. It's just, there's a lot more digital outputs and a lot more analog. I wouldn't say there's more analog inputs than digital inputs, but you're going to have way more analog inputs than analog outputs. Special modules, that whole paragraph on page 17 is highlighted. While discrete numerical and analog modules handle a majority of PLC interfacing needs, there are occasions when specialized devices may need to be connected. These situations are covered in different kinds of specialized modules. Examples include high-speed encoder counters, servo control, stepper motor control, synchronized access control, velocity control, temperature monitoring control, and smart transmitters. Key in on that temperature monitoring control. That's what I was talking about, where you have like an RTD or a thermocouple card. Page 18. They go through each bullet point. The whole temperature monitoring control bullet point is highlighted. Out to the side of that, I wrote special module. So temperature monitoring control modules. These modules condition inputs from thermocouples. The thermocouple signals are filtered, amplified, and converted to a numeric value by an ADC. Key in on the next two sentences specifically for this. The numerical values for each input are processed by an internal microprocessor as an input to the PID loop. The processor executes a PID algorithm on each input. Key in on those two sentences. The output of each loop is sent to the PLC as both a numerical value and a time proportioned output TPO signal. PLC program can either can send either the numerical value to an analog output module or TPO signal to a digital output module in order to close the loop. 336 PLC communication modules. Third paragraph, right where you see Ethernet and Wi-Fi at the end of the paragraph is highlighted. Ethernet and Wi-Fi are currently the most common networking technologies providing wired and wireless communications respectively. Many PLC processors have a built-in Ethernet port. Most everything you're going to see now is all Ethernet. Used to be like you would have like Modbus and Profibus were pretty popular for a while, but Ethernet's gotten so fast and so easy and everybody uses it. That's why like these are all connected with Ethernet rather than a different it's called protocol. Top right of page 19, that sentence that has serial network is highlighted. Many PLCs also communicate over a serial, that is a super old statement, over a serial network such as RS-232, 422, and 485. Anybody mess with an older, everybody's had an older computer that has like the big plug-in that has all like, I think there's like 30 something pins on it and you have to like line it up. That's a serial network. So like normally the processor of this would have like a big serial connection, and whenever I was in college, like that's what we used to upload our stuff to the PLCs and stuff like that. That's old. Everything's Ethernet now, but still might need to know that. Nothing in module addressing. Take a couple minutes and answer those 6 questions on page 20. That gave me. Alright, section 4. PLC programming. So you're going to have different types of languages that you can program PLCs in. 410 PLC programming languages. I've got all 5 of those bullet points highlighted. Ladder diagram, function block diagram, sequential function chart, structured text, instruction list. Out to the side of that, it's about the dumbest, not the dumbest, but it's a dumb practice test question. Write no LI. There's no PLC language called like ladder instruction or anything like that. There's no LI. And then online, separate but same highlight, online test question. You need to know that there's 5 different languages. So I just wrote that out. I wrote in my book, I just wrote a little asterisk out to the side and I wrote 5 different languages. 411, ladder diagram. First sentence is highlighted. LD programming, also known as ladder logic, is the most widely used and oldest form of PLC programming. That's because whenever everybody switched, they showed me. Whenever everybody switched from like relay logic, which is all hardwired, to PLCs, it's still way easier for me to read ladder diagrams. It will be for y'all as well after doing like the PLC or the motor control lab, because it looks like this. Like your ladder diagram stuff looks like this, and it's easier to read for basic stuff. So that's why it's the oldest and still most widely used. Function block diagram, 412, first sentence is highlighted. FBD program is a lot like creating an electrical schematic. I wish they had pictures of it. Nothing in sequential function chart. Moving on to 414, structured text. First 2 sentences of 414 are highlighted. Structured text is similar to many mainstream computer programming languages. ST programs resemble English and can be understood to some degree just by reading them. So if you've ever, I don't know if anybody ever written computer code? Like you can actually use words and stuff like that to write computer code, and that's what you can use structured text in instead of like ladder logic. If y'all get into PLCs, ladder logic is probably where you're gonna, at least that's definitely where you'll get into it. And then like I've dabbled a little bit into the function block diagram on one of the lines that I used to work on. Function block diagram just it works even faster than ladder logic or ladder diagram just because of how it's set up, and that's the advantage of it. It's super fast. 415 instruction list. First 4 sentences are highlighted. Like structured text, instruction list programming is a text base and is done with a text editor. Unlike structured text, instruction list is essentially only readable to experienced programmers. Each program line is a short, abbreviated instruction called a mnemonic. Most are just a few letters long and look like LD, ST, and JMP. Development tools, 416, top right of page 22, first 2 sentences are highlighted. Besides these basic tasks, some manufacturers also offer a PLC simulator that mimics the basic functionality of the PLC on a regular computer. Simulators can be used for program testing without the need for an actual PLC. When I was in college, I learned on Allen Bradley PLCs, they definitely have a simulator, and that's definitely good to try out before you upload your program or download your program into a PLC, just to make sure everything's functioning correctly. At work, we used GE PLCs, and they had the same thing. Like they had simulators. Some of the cheaper, like if you go out here and see like the little smaller trainers and stuff like that sitting on the benches, like those have Automation Direct, which is like the Harbor Freight of electrical components. Those will not have a simulator built into them. Those are pieces of junk. That's why we don't use it. 420, ladder diagram programming. 421, relay. On page 23, first full paragraph on page 23, first sentence is highlighted. Outputs from PLC output module are shown as a coil on a ladder run. So I said circle. This is really what the outputs look like. Standard output, a latch, and an unlatch. A lot, not all of y'all, but a lot of y'all have been on the motor trainer, and like you've had that auxiliary, remember having the auxiliary contact, and I said that was the latching function? In a PLC program, you don't have to write like another thing, you just have to write the output as latch, and then you would have a separate rung that would be unlatch. So you would connect like a normally open push button to this to latch it, and then you would have another normally open push button on this separate run to unlatch it. So there's a little bit of variance in how you write code versus how it's actually shown like an actual ladder diagram, which everything's hardwired. Same paragraph, right after where you see the word false in all uppercase, I've got the next 3 sentences highlighted. A latch coil is shown like a standard coil with the letter L in the center of the coil. When a rung is true, a latch coil will energize. When the unlatched coil, the coil with the letter U is in the center with the same address, is energized, the latch coil will unlatch. Timers and counters, 422. Second paragraph, the whole thing is highlighted with, you're gonna have 3 separate questions come out. The operations of a software timer and counter are similar to that, are both in that they are both counters. A timer counts the number of times that a fixed interval of time, such as 1/10 of a second or 1 second, elapse up to a preset value. For example, to time an interval of 3 seconds, a timer counts 3 1-second intervals. A counter simply counts the occurrences of an event. Key in on that sentence. A counter simply counts the occurrences of events, and then the rest of the paragraph is also highlighted. Both the timer and the counter instructions require a register location in memory to store the elapsed count and another register to store the preset value. Preset value will determine the number of event occurrences or time intervals that are to be counted. They go through and how they write through counting up and counting down. I don't have any highlights on pages 24 and 25, but they talk about how that stuff is done. You have arithmetic functions 4, 2, 3. So you can do addition, subtraction, multiply, divide, all this stuff. You're usually using that for like product supply. Like a lot of times, all the way at the end of an assembly line, you'll see something up there like we put out this many units today, or something along those lines. That's where they're doing the arithmetic stuff. Nothing highlighting that. Page 26, data comparison. 424, second paragraph, first sentence is highlighted. In the latter language, there are 3 basic data comparison instructions: equal to, greater than, and less than. I don't have any more highlights on pages 26 and 27. Yep. Going on to page 28. Guidelines for programming and installation. This is important because there's a lot of times people can write code that makes sense to them, and it's super confusing to everybody else. Like you can get 2 separate codes to do the same exact thing, and one code can be 8 pages long and the other code can be 1 page long. If you're the person coming in behind them to troubleshoot stuff, it's way easier. The more simple stuff is, the better it works. The more complicated you get, the more stuff that's going to hang up and go wrong. Simplicity is key for programming. In 431, the programming section on 28, I just have the heading of the first bullet point highlighted. Determine the control task. Out to the side, I wrote first step. That's the first step in programming is, what do you want to do? Determine the control task. First step, what do you want to do? 432, installation. First sentence is highlighted. Use the following general guidelines to install a PLC. First bullet point's highlighted. Make sure the PLC selected has 25 to 50% extra capacity for future expansion. That doesn't apply to micro PLCs that are just doing small one things, but having something like this, like you want to make sure that you have, like you're not filling up all these cards, at least not all the way to the end. Like you want to leave, you're always going to add stuff. You also have, like a lot of times they'll sell you this whole rack with different cards and stuff like that, and if you, like these cards go bad. Like we had to replace one of these cards in the methanol plant, trying to get it up and going back there. But we had an extra one, I think in this rack or another one we had on campus, but about $4 per card. So when you order this stuff, order spares if you end up being in that side of stuff. 433, input output wiring. Second set of bullet points on the right hand side. Highlight where it says use the following general guidelines to make static input wiring checks. The last bullet point in that section is an online test question. Take precautions to avoid injury or damage when activating input devices connected to series loads that are external to the PLC. Take precautions to avoid injury or damage when activating input devices connected in series with loads that are external to the PLC. All right.